All right. So taught this course a few times, and students sometimes feel that they don't quite get it, right? And I put things, some little comment will come up or some little test question will come up and everybody will bomb it. They realize, well, they don't quite get this, right? So we just keep going over the same material, right, over and over again. And I do hope that you let me know, hey, this piece didn't really add anything, right? All right, so anyway, what are we saying here? We're saying in this example, we're going to have a universe of 0 through 3, and we're going to have some relation alpha that's going to tell us for every value of x and value of y whether it's true or not. Right? Everybody got the setup here? Right? And right, so for example, 0, 0 is true, 0, 1 is not true, right? And right, so now we can think, right, what are the possible inputs to this, right? Well, 0, 1, right, is an input. There we go, we have them all, right? If you've taken pin 19, this is a set of what? It's a set of tuples of length 2, where each guy is 0 through 3, right? And you can see you can take the set 0 through 3, cross the set 0 through 3. If you remember that notation, right? So here we got the set of tuples, and it corresponds, of course, to this matrix, right, where we have a value for each of them. All right. Now, we're going to want to talk about this alpha. We want to say things about alpha. So one thing I might want to say is, look at that column where y is 2. I want to claim everything in that column is a 2, right? But I don't, and I want to say nothing about things outside of that column, right? I was going to ask you how to do it, but there it is, right? I quantified over the alpha 2, but sort of saying, if we care about the alpha, right? The point is that there are a lot of alphas that we care about. And which ones do we care about? Care about those that for all x of 2 is true, right? Everybody get that? Yeah. All right, given arbitrary alpha we care about, right? That's this fixed value 2, that's that for all x, you give me an arbitrary x, and the statement's true. Yeah. Alpha? No, alpha is this relation, and we don't know offhand which ones are true and which ones are not true. So there's many of such alphas, and I'm just trying to communicate to you which ones I care about. Yeah, it maps x, y to true, false, right? Yes, yeah. So in fact, each of the tuples here is an input, and so I'm going to say for all of these inputs, the answer is true, right? Everybody good? So that's, I don't know, that's what it says. All right. Now, what happens if I just want to tell you that one of the columns is all true, but I don't want to tell you which one, right? Then what do? We say for all the ones we care about, there is a y, right? We could call it y sub exists. There's some y such that for all x it's true, right? Everybody see it saying that? What happens if I want to say the diagonal is true? Right? Then I say for every x, alpha xx is true. Right? I'm telling you something about my alpha. I'm telling you that the diagonal is true. Right? Here's a funny one. I want to tell you that, right, this is just saying for every x, the sort of off diagonal, the x and the x plus 1 is true, right? And I did it mod 4, so it wraps around, right? Now, I could give you some arbitrary function f from x to y, yeah? Yeah, you could just remove the mod 4, and then x plus 5, x of 3 plus 1 would be 4. And then I guess you would be saying that 3, 4 was true. Now, if you were running some sort of Java program, maybe it would crash, but maybe the logic wouldn't mind that you went outside of the range. I don't know. I did it to make sure we didn't go outside of the range. Right? I mean, it's 3 comes up, right? So then how does your logic does it get upset with that? I don't know. Right? Here it's just some concrete, right? This is some function from x to y, right? And so for x equals 1, we go over to 0 and we get 1, 0 is true. Right? These all making sense to people? Right? Right, now this is kind of a funnier one, right? Yeah. All right, this page here. This one. Right, this was the diagonal. And this one here. This one says I'm not, right? So I'm not telling you which diagonal, right? I'm just saying I'll be happy with your alpha if there's, oh, sorry, I'm not telling you which column, right? I'm not telling you which column. I'm just telling you I'll be happy with your alpha if there's some column that's all true, right? So this is, how do we say that? We say there exists a y, right? There exists some column such that for every x, it has to be true, right? So in this one, right, there is some function that works here, right? For all, we want to say there exists some function that's that for all x, x and f of x is true, right? So you can see a little picture here. Those go back and forth, right? Every we're saying every x, there's some function that maps these x's to true things, right? Everybody see that? And here, right? Well, of course, the function depends. Yeah. Now, what we're doing here is somehow that, right, the adversary has to come up with the exist. So it's coming up with this entire function, right? And in fact, what we're kind of studying is called first order logic. And in first order logic, your object, your x's, are objects. And in second order logic, they're functions, right? So we're kind of, if we write this down here, if there exists a function, then really we're doing second order logic. And is that a disaster? Nobody told us we had to do first order logic. Right? So what we could do instead of, in this game, I come up with this function and then you give me an x, and it works, right? We can not kind of give the whole function. right? So here, what happens in this game, right? So I guess here I made it green. Anyway, somewhere we get an alpha, right? And then we get an arbitrary x. And now I haven't told you the function before, but now when I know x, I know I can map it to, right? So, right, does that make sense? And so the point is that this line is the same. Which we don't have here. Everybody good with that? All right. So in three-dimensional space, right, we have a little bit more confusing, and they're n-cubed tuples, and then, right, four-dimensional space, and all right. So everybody remember which, in this case, both this and this are true, right? Yeah. Neural nets, if their thresholds will be true false, but I'm not sure what. Yeah, I'm not sure what the question, how to answer it. Yeah. 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 Yeah, certainly logic is useful in all these things. And I love to talk about neural nets, but let's not do it right now. Yeah. Yeah. No, there's no chalk. Oh, here's one. So here, I'm going to give the punchline of some of what we were doing up here. In fact, that we're going to give it at some point over and over. I think we've given it a few times, that these two lines are equivalent. So this one says, here are all my x, here's all my y, and I tell you the function that maps everything here to over there, right? And then for every x, xy is true, right? Well, this one, I'm not giving you the whole function, but I'm saying you give me the x, and then I'll come up with the function just for that x, and it's true. So these two lines are the same. So that, I don't, yeah. Yeah, yeah. So x isn't true. The x of f of x is true. You need a y before you know it's true. Hmm? So look at this picture here. It's true. The statements, both of these statements are true, right? Because for every x, there is a y. And there's a function from x to y, right? And when is it true? It's true where it's basically saying for every row, there's something, and there's a true in every row, right? For every x, there is a y for which it's true, right?